Good morning everyone, and welcome to today's worked exam answer video. Today I'm going to be having a look at an AS level structure and bonding question, which of course will need to be understood by year 13 students as well. We're looking at two organic compounds here. We're looking at pentan-2-ol and pent-1-ene. We've been given the boiling points of these two substances, and we have to explain why pentan-2-ol has a higher boiling point than pent-1-ene. And I guess the first thing is I've said that this is a structure and bonding question. However, there is no reference to structure or bonding in this question at all. So the first thing that I guess we need to understand and appreciate is that anytime we are thinking about melting and boiling points of substances, structure and bonding has to be a topic that comes to mind. So we've got pentan-2-ol, which is an alcohol, and for those of you who have not yet moved on to alcohols, I'll draw the structure of the pentan-2-ol so that we can see what type of intermolecular forces there's going to be. The boiling point of pentan-2-ol is 119 degrees, so a lot higher than the boiling point of the pent-1-ene, which is an alkene, which only has a boiling point of 30 degrees. And again, I will draw the structure of pent-1-ene so that we can compare that with the pentan-2-ol. So, pentan-2-ol is an alcohol with 5 carbons, and the 2 tells us that the alcohol group is on the second carbon, which is an O and a H, and then all the rest of the bonds from the carbon atoms will be hydrogens. And then pent-1-ene, 5 carbons again. The 1 tells us that the double bond is between carbons 1 and 2, and then because it's an alkene, it's a hydrocarbon, and so all of the other bonds will be to hydrogen, like so. Now they've tried to keep the overall MR of these compounds quite similar. We can't keep them exactly the same because we have an extra oxygen, well, an oxygen in the alcohol and an extra hydrogen, two extra hydrogens actually, that we don't have in the alkene, but we do have the same number of carbons. And the reason why I've mentioned that is because the van der Waals forces between the molecules, so the van der Waals intermolecular forces, they get stronger as the MR of a molecule increases. So that's not really the thing that they're looking into here. The other two types of intermolecular force that we need to be aware of are permanent dipole-dipole forces and hydrogen bonding. And I guess I should really go back a little bit because I've started mentioning intermolecular forces but haven't really said how I know that intermolecular forces is what we need to consider here, because some people would be thinking potentially about the types of atoms and the strength of the bonds between the atoms in these two different molecules. Now, I've used the word molecules a few times, and the word molecule can only be used if we have non-metal atoms joined together by covalent bonds, and each molecule is made up of a fixed number of atoms joined by those covalent bonds. If we have molecules and we have covalent bonds, the only two structure types that we can be considering would be giant covalent and simple molecular. And our giant covalent structures, whilst we can call them macromolecular, that's a term I don't like, we're not thinking about molecules. Giant covalent structures will only be diamond, graphite, silica. There are a few others, but they're the main 3 that you need to be aware of. And then any other structure made up of non-metal atoms joined by covalent bonds will have simple molecular structures. And with simple molecular structures, we're not breaking the bonds inside of the molecules, we're overcoming the intermolecular forces between them. So there's 3 types of intermolecular force. There's the van der Waals forces, which I've already alluded to. They're going to be quite similar here because the MR of these two molecules is very similar. All Simple molecular structures will have van der Waals forces between their molecules, they're universal, and that's because they are generated by the movement of electrons, and all molecules will have electrons within them. Not every single simple molecular structure will have permanent dipole-dipole forces between the molecules, and not all of them will have hydrogen bonding. So to have permanent dipole-dipole forces, we need to have within the molecule at least one polar covalent bond, and we need there to be regions of more partially negative charge and regions of more partially negative charge. And that's caused by the difference in electronegativity of those atoms within that polar bond. In pent-1-ene, we do have different types of atoms. We have carbon and hydrogen, but their electronegativity values are extremely close together. So this as a molecule would overall be non-polar, and each of the bonds within that would also be a non-polar bond. So there's non-polar bonds, and overall it is a non-polar molecule. So that will not have any permanent dipole-dipole forces between the molecules, and therefore cannot have any hydrogen bonding either. Because hydrogen bonding is a very extreme case of permanent dipole-dipole forces, where the bond is so incredibly polar because we have one of the three most electronegative atoms, which are oxygen, fluorine and nitrogen, bonded to a hydrogen. And we have one of those in our pentan-2-ol. So the oxygen is so much more electronegative than the hydrogen here that the electrons that are shared between those atoms in that covalent bond will sit very, very, very close to the oxygen. So the partial negative charge on the oxygen will be very, very strong, and the partial positive on this hydrogen will be very, very strong. And in another molecule of pentan-2-ol, we will then have the oxygen of that OH using its lone pair to attract the delta positive hydrogen here, and that will be our hydrogen bond. Now, I don't like the fact that we call it hydrogen bonding because it is an intermolecular force and not a bond, but that's just something we're going to have to get used to and deal with. So hydrogen bonding is an intermolecular force between the oxygen lone pair, which will be very delta negative, and the delta positive hydrogen of different molecules. Now that is a lot of background to enable me to answer this question. So we have to explain why pentan-2-ol has a higher boiling point than pent-1-ene, and the question is worth 3 marks. And there are a number of questions that exist like this where you are comparing two different substances by thinking about what forces we are overcoming, and thus why one has a higher boiling point than the other. So this is quite a common question. So what we're going to need to do is we're going to need to specify the strongest type of intermolecular force that we have between these molecules and between these molecules, and then state which of those forces is the stronger of the two. So the first thing I'm going to say is that pentan-2-ol has hydrogen bonding between its molecules, and that will get me the first mark of these 3. Whereas pent-1-ene only has van der Waals forces between its molecules. So that's got me 2 marks because I've stated the strongest type of intermolecular force present between each of the types of molecules. There are no other intermolecular forces here because of the non-polar bonds. Here we still have van der Waals forces, but it's the hydrogen bonding that's way more important because hydrogen bonding is the strongest type of intermolecular force. Permanent dipole-dipole forces are in the middle, and then the weakest are van der Waals forces. Now that doesn't mean that you can't have a very, very, very large molecule that might only have van der Waals forces having a higher melting or boiling point than a substance that has permanent dipole-dipole forces. But if we have a really similar MR, like we do here, the van der Waals forces are going to be much weaker than the hydrogen bonds. And the third mark is for making that kind of statement. Now you can say hydrogen bonding is the strongest type of intermolecular force, because by saying it's the strongest, you're kind of also saying that the van der Waals forces are weaker than the hydrogen bonds, or you can say that the hydrogen bonding is stronger than the van der Waals forces. So you can use the comparative language, which if we were comparing permanent dipole-dipole forces with van der Waals, I would definitely use. But because the hydrogen bonding is the strongest type of intermolecular force, you can just state that for the third mark. So hydrogen bonding is the strongest type of intermolecular force, hence why the boiling point of pentantuol is higher. Job done. Now, the actual answer itself is quite nice to structure. It'll always be those 3 marks if we're comparing the boiling points of 2 different substances. It will be the strongest force in each of them to get a mark, to 2 marks in total, 1 for the alcohol, 1 for the alkene, and then the third mark will always come from comparing the strength of the intermolecular forces that you've mentioned. The difficult part here was, first of all, recognising that that was the path we needed to go down, that we needed to be thinking about intermolecular forces. Then we needed to know quite a lot about intermolecular forces to be able to spot what types were present. So apologies for sort of explaining that and explaining a lot of the context of that, but actually I'm not sorry, because that is fundamental understanding that we need to have to get to this answer. If I'd have just written the answer, then that might have left you with questions as to how I knew that it was hydrogen bonding and van der Waals, and how did I know that intermolecular forces were what were required. So hopefully you'll agree that it was worthwhile me giving all of that background. I hope you found this video useful. Any questions, as always, please just ask. You can leave me a comment on the video, or you can send me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys, and for all your support with my worked exam answer videos. It's really appreciated. Hope you have a really wonderful day.